So good morning. My name's Matthew Realff. I'm a professor in the School of Chemical and Biomolecular Engineering. And as you heard at the beginning of the session, Michael refused to allow anyone to use slides. And I'm one of those people who finds that an extremely scary proposition. So in fact, what I will do, of course, is to read from a prepared script instead, thereby frustrating Michael's desire to have a less formal presentation. So, if you look across the street, you'll see W21. It's one of the many parking lots here at Georgia Tech. If you look closely at the very edge of that lot, there are a few parking spaces with electric charging hookups. Most of the parking lot does not have these chargers, and it would be difficult to install them without adding significant electrical distribution. This reflects the fact that about 0.5% of the American auto fleet is electric vehicles, and the challenges that would be involved in having significant adoption. It's not just a matter of consumers choosing to buy electric vehicles. There are substantial issues with the grid and distribution systems required to support this shift. Is there an alternative that might result in less disruption and still prevent the rising atmospheric CO2? What if instead of electrifying transportation, we figured out a way to use this infrastructure but ran it on renewable electricity? What if instead of electrifying transportation directly, we used renewable electricity to make drop-in replacements for fossil fuels? Drop-in renewable fuels would provide a pathway in which consumers are not required to change over their cars or trucks, nor are we required to expand the distribution infrastructure for electricity. Instead, the electricity would be used where it is generated to make fuels, and the existing pipeline and distribution infrastructure to bring these fuels to consumers. This would have the advantage of using our existing infrastructure for producing and consuming fuels, which is a significant investment. A recent analysis carried out by Kerry Metz and Rich Simmons of the Strategic Energy Institute here at Georgia Tech has revealed that this is valued at around $8.5 trillion. A large fraction of this is in the transportation assets themselves: cars, trucks, ships, buses, and aircraft. But as much as $2.5 trillion is in the petroleum and natural gas supply chain itself, a significant investment that could be leveraged for a more sustainable solution. A second advantage that this interconversion of renewable electricity and hydrocarbons provides is storage, and Rich already spoke to the issue of storage this morning. Most low-carbon future scenarios envision very high levels of renewable electricity, which will need to store over daily cycles, but also over seasonal variations. Sunlight varies significantly between summer and winter in the US. For example, in Arizona, the winter sunlight per month is about half that of the summer peak. Therefore, to provide similar energy in December as in June, which reflects current Arizona generation patterns, would require significantly higher investment in solar production and lead to excess power availability in the summer months. We could use this extra energy to make fuels, storing energy very cheaply for use at other times, and allowing energy to be harvested efficiently and moved geographically to other regions where renewable power is less easily generated. The production of drop-in fuels from renewable electricity requires 3 steps, and I'll briefly describe each one: its role and current maturity. To make a renewable hydrocarbon fuel, you need sources of carbon and hydrogen. The source of carbon should be renewable, abundant, and available anywhere we are producing electricity. Our proposed solution is direct air capture of carbon dioxide from the atmosphere, referred to as direct air capture, or DAC. This satisfies the above criteria and has one added advantage. If we build DAC systems to recycle CO2 from the air, we can use this as a way to build the infrastructure from removing CO2 from the atmosphere and sequestering it. It is my belief that we will need this infrastructure because negative emissions in the second half of this century are envisioned in most pathways to meet 1.5 warming goals. Renewable fuels will provide a pathway where we can monetize the CO2 for fuel replacement in the medium term and then draw off a side stream as our need for hydrocarbons falls if we transition to another energy carrier, such as hydrogen or electricity. Otherwise, we can expand the DAC deployment and keep using renewable hydrocarbons, but the cost of the expanded infrastructure will be significantly lower, having driven down the cost along the learning curve. The second component is the reduction of CO2, either directly with electrolysis or indirectly by making hydrogen from water and then using the hydrogen to reduce the CO2 chemically. In either case, the reduction of the CO2 will be by far the most energy-intensive step of the process. The electricity use of the DAC system is estimated to be around 3 kilowatt-hours electricity per gallon, and that for electrolysis to make hydrogen, approximately 60 kilowatt-hours per gallon, 20 times that of the DAC system. Once the CO2 is reduced, it is in a form of a small molecule like carbon monoxide, methanol, or possibly methane or ethylene if fully reduced. These molecules are used in existing chemical processes to make hydrocarbons through, for example, Fischer-Tropsch or methanol to olefin pathways. The maturity of each of these technologies is different. For Fischer-Tropsch or methanol to olefins, there exist chemical facilities that practice these at scale today. Electrolysis using PEM or alkaline fuel cells has been demonstrated at 100 kilowatt to megawatt scale, but needs to be deployed at 1 or 2 orders of magnitude larger scale. And other approaches such as solid oxide electrolysis cells, SOECs, are yet to be built beyond the pilot scale. Similarly, DAC technology is at the pilot scale. For example, Global Thermostat, a company with research labs here at Georgia Tech, using adsorbents applied to monolith contactors using techniques pioneered by Professor Chris Jones in chemical engineering, has a pilot facility in Huntsville, Alabama that has just started up. What will renewable fuels cost? Using engineering estimates based on initial pilot and literature studies, a range of $2 to $6 a gallon to produce the fuel is found. This comes with an estimated $2 to $3 trillion for the capital investment to replace all the US hydrocarbon fuel volume, not including the investment in renewable power infrastructure, but pricing electricity between 2 and 6 cents a kilowatt hour. And we heard from Ajit this morning that that seems very reasonable for a power cost for renewable PV. This is significantly more expensive than fuels today, which sell for values in this range, including the taxes, distribution costs, and margins of the producers. In a study performed by Professor Emanuele Massetti of the School of Public Policy, he estimated the consumer willingness to pay on different prices for crude oil and carbon taxes using a simple partial equilibrium model. He found that with costs of oil at $100 a barrel and carbon taxes at a cost of $100 a ton, that the consumer would have a willingness to pay of about $4 for renewable hydrocarbons. This is beyond the price of oil in the foreseeable future and taxes proposed today. So clearly we will need to have cheaper infrastructure if we're going to make this practical. So what next? At Georgia Tech, we propose to do 3 things. First, we believe we should construct an integrated pilot that demonstrates air capture to fuels. We have the faculty, staff, and student expertise and talent to do this. We have cutting-edge research in air capture led by Professors Chris Jones and Ryan Lively. We have electrochemical systems experts in Paul Cole and Mei-Lin Liu in CHBE and MSE, as well as numerous others in electrochemical and catalytic space, such as Joseph Sadeghi in chemistry and traditional catalysis and reaction engineering with Carsten Sievers and Michael Filler, again, from chemical engineering. Second, we believe that understanding the macroeconomic and policy implications of renewable fuels using integrated assessment models will be vital to framing their value to defossilizing the transportation sector, a charge that Professor Massetti will lead. Finally, we believe that a multi-institutional approach to the research and engineering challenges is important, and we are collaborating with organizations such as the National Renewable Energy Lab on their lab initiatives that intersect in this area, such as electrons to molecules. Drop-in renewable fuels. Recycling CO2 from the atmosphere using renewable energy is a circular approach providing a parallel pathway to photosynthesis to close our carbon cycle and retain the value of our existing infrastructure while blending away fossil fuels. It's an exciting frontier for sustainability research at Georgia Tech. Thank you.